Really, really basic ideas here. If I start with a graph, let's say these two. H of x is x squared plus 2, and g of x is x, the quantity x minus 2, quantity squared. What I want to do is figure out what is the parent function of either of those graphs, as well as what was any shift that was done to them to generate the graphs. And I know, Caleb, you were talking when we did this a week or so ago about the roots. You're just making the perfect roots and stuff like that. It's the same basic idea. So if I'm looking at both of those graphs, what would be the parent function? X squared, right? The parent function here is just plain old boring x squared. We all know put these both in the same. We all know that an x squared graph is a parabola. We use perfect squares. Well, we pick 1, 2, 3, basically then we're off our graph. We did it on both sides because it was symmetrical. It was symmetrical about that, what we called an axis of symmetry. There were many, many, many different ways to find that axis of symmetry when you graphed quadratics. You did the opposite of b over 2a. If you had the vertex form, the a, h, and k, the axis of symmetry was your h value. If you had intercept form, we had your two setups for zeros, you would take the midpoint. We'll talk a little bit about the different ways to go as we go through this. The parent function, I'll put in black, we had 0, 1, 1, 2, 4, 3, and 9, and then it mirrored. And this was never a problem for you guys to graph. That's something what you guys have done for a long, long time. What's that? Oh no, it was honest. I wasn't sarcastic. There was no sarcasm intended. You might need two. Yeah. Here you go, guys. You might need, grab 2 if you can here. All right. Now, you guys, when we first did some graphing stuff, you asked me, oh, do I have to graph that parent function? You want me to show the shift? At that point in time, I was like, it doesn't matter if you want to jump right to it and pick your order pairs, it wasn't a big deal. But now that I start talking to Mr. Fontana a little bit, he and I have come to the rationalization that graphing probably wasn't your favorite thing to do.
You just now came to that realization?
Well, I took it for granted that it was pseudo-enjoyable or somewhat normal or whatever. So what I want to do here is have us plot the parent and then realize what is happening to the parent graph via its shift. So,
wait, the g of x is the shift?
h of x and g of x are just 2 other equations that have the same parent function. I'm going to show you guys to remind you what they are doing in terms of the shift. Okay, that's all I'm talking about.
I thought that, like, okay. Oh, that makes sense.
So if I'm looking at x squared plus 2, if I take that parent function, what am I doing to the parent function here? So what direction is the parent function moving? Up 2. It's moving up 2 because the squared term is still here, which means that that plus 2 is playing the part of what? H or K? It's vertical. This is your vertex form of a parabola. All right? Where your H and your K are your vertex. Your axis of symmetry is x equals h. Your axis of symmetry always goes to the x coordinate of your vertex. Always, always, always. H was your horizontal shift. K was your vertical shift. did A do? Remember? Yeah, it's kind of like the slope of how wide it is, or how narrow it is, how skinny or fat it is. It's, if you want to think of it in terms of slope, but it also tells you up or down. So A is like your direction, and what do you want to call that? Openness? Or width? Widthish? I don't know. Width? Sure.
Wait, what are you saying? Wait, what do you mean?
How wide it is, opening up, or how narrow it is. If the A value is really great, it's more narrow. If the A value is really small, it's more open. Think about it.
Sure.
It really doesn't matter. So basically, we'll just think of it as direction. And we'll call it a scalar. Like for your multiplier, like kind of like slope. We'll call it slope-ish. We know it's not the slope because it's a curve, but can I call it
That's
slope-ish?
too much. I'm just gonna.
Whatever. All right.
Scalar. Wouldn't it be scale B?
I think scalar is when the math term is AR.
It is a math term?
Yeah.
I think he's saying it's a math term just so he's right.
Look it up. Right now. Google it.
I'll Google it.
Scalar multiple. Scalar.
I'm just gonna trust you.
Great. So this one tells you that your vertex has just moved up 2 spots. Your H value is still at 0. The K value is at 2. It still has the same exact opening pattern to it. It's just a matter of taking each and every one of your points of your original function and moving it up 2. And that's all it does. Okay? It just moves it up.
I'm really proud of my graph and Cameron's data.
Good job.
How like symmetrical and everything.
Looks fantastic.
I know.
What about the quantity x minus 2 squared? Where does that one go?
Shifted to the right.
Ah, see how it's inside the parentheses? It's inside the parentheses, which means this value of 2 is playing the role of h. Therefore, since it's x minus 2, that means that my h value is 2. Horizontal is left and right. Okay? This one is going to go to the right, 2. So the original graph of x squared, all of those points then just move right 2.
So honestly, it's just like an extra step.
Are we
That's all
gonna
it
have
is.
to do this on the test?
Wait,
That's all it is. I'm starting reading, yeah.
why wouldn't it be 4 because of the square on the outside? Wouldn't it just go to the negative 2 and then times the Wouldn't it be negative 2 squared because 2 on the outside of the parentheses?
Yeah, what's negative 2 squared? 4. But negative 2 minus 2 is negative 4. Negative 4 squared is going to be way out here, up 16. It's just not on the graph.
No, I think he's saying that
You're saying you square.
it needs to be moved over. The h should be 4.
Yeah.
No, it's this value here is the shift. That's just all it is. It's just moving this over to the 2. That's all it's doing. Okay? Because if you take your excuse me, we're just moving horizontally left and right. We're not moving up and down. We're not opening or closing it anymore. We're just shifting it to the right. That's all this is doing. Okay? That's all that we're doing here. Okay? Sir.
Wait, like how did you grab how do you do it again?
The original graph was x squared. H tells me to move it over to the right 2. That's it. That's it.
So
What were, a point of what? It was just 2 different functions. That's all it was. All we're looking at here is just a reminder of what these things do. The parent graph for this is y equals ax squared. Okay? That's the parent graph with the a value thrown in there. When you shift it, h moves you left or right. K just goes up or down. That's all I wanted to show you with a parabola graph, because I know you guys all did that last year. You might have done it with the conic stuff too, that 4py. All right. Everybody probably also did it where you had the x minus h 20 squared was 4p y minus k. That was we all did that in conics. So I know everybody did just regular parabolas up and down, left and right like that. I know honors guys, we did all the shifts with all the different conics. So this was just one of them that we worked through, okay? That's all I'm looking at. That's it. Just to remind you guys of what that looks like. What's up? All right. Okay. When we go to the next one, just so you remember, when they're talking about it in terms of function notation, when they're adding stuff in, subtracting stuff out, putting stuff within parentheses, all that stuff, it's just a matter of where things are going. So here, if you have any function, whatever it is, if you tack on something at the end of it, like plus something, it's moving up. If you subtract something at the end, it's moving down. If you group it within the parentheses,
Wait, so like,
moving right.
something is written as f of x plus 6, and we were supposed to.
You take whatever the f of x was and move it up 6. For example, if f of x here was, let's say, the square root of x. Okay? We'll say f of x with the square root of x. And I want to take and make this function g of x by taking f of x and adding 3 to it. If I look at it in terms of functions, all this is telling me to do is that my f of x equation was the square root of x, and then I add 3 to it. That's all that means. Now, when we're looking at the square root of x, do you guys remember the values we used for those? Yeah.
So, if you give me just x, the inverse of x is
Yeah.
oh.
I'm not doing any inverse here.
No, because you put that.
Okay. What I'm looking at here, as far as parent function and shift, f of x is playing the role of the parent function. Parent function in this case is square root of x. Square root of x graph looked the same every time. You started at 0, 1, 1, 4, 2, 9, 3. And that's how we plotted a square root graph. We connected these lines with a dot because that graph wasn't technically there. We were using it to base our shift off of. Okay. To each of these points, when it's tacked on at the end, that, remember, it's not grouped into parentheses. This is a vertical, which means it goes up 3. So all you had to do was take all these points, move them up. And you did that. That wasn't anything new. Okay? What they're trying to show you here in terms of function notation, go back to this, I skipped it. What they're trying to show you here in terms of the function notation is how a second graph is obtained by taking a parent function and moving it. That's it. Taking the parent function of x squared, adding 2. So that means x squared plus 2. That's all it means. What was the parent function and what's its shift? That's it. You guys did every one of these problems before, but it's just written here, that's all. Notice your horizontal shifts are thrown into parentheses. That's how we always found horizontal shift. If it was grouped within parentheses, you knew things were moving left and right. If it wasn't, you knew it was a vertical. It was your K value. That's the only thing that's new is the fact that they wrote it in terms of functions. Okay? So it shouldn't be frightening. Nope. I'll show you another one. Let's look at this. Let's use f of x equals x cubed to graph these other two shifted graphs, which means x cubed is our parent function. Now, obviously, when you're using x cubed, it's going to be tough to plot every number on there because, well, what's 1 cubed? What's 2 cubed? What's 3 cubed? That's a little bit off my graph now, isn't it? A smidge. You can go by 3s, but it's kind of faint. So you start to sit there and plot some values that really make sense. If I'm going to shift this, move this up, we're going to use our parent function. My parent function is x cubed. Well, start at 0. What's 0 cubed? So I have 0, 0. What's 1 cubed? And then 2 cubed was 8. What's negative 1 cubed? Negative 1. And then 2 and negative 8. So you've all done that graph. That's nothing new. You've also all done the parent part of this, dotting it out. Now, according to this, what happens to it at g of x? It just moves all of those points down one spot. Now, after you plotted your parent function, when you plot your other one, just move them down one. And what do I do with the line then? What is it? As a rock. That's why things love you.
Like instead of doing stuff like that, if we just got like.
That's fine. Technically, it should be a dotted line because it's not really there. Parent functions aren't really there. They're just they help us to do the shifts. Remember last year when you guys graphed trig, sines and cosines and all that? One of the reasons why we plotted the parent function because it's so much easier to get those intervals and those breakpoints to know how to add and subtract in pi's and pi over 2s and all that stuff. It's the same basic idea. It's there as a help to plot your points. It really is all it is. Okay? And now with the second one there, that h of x is the quantity x plus 2 squared plus 1. There, and up 1, good. I was just going to say there are two different things that are going on. You have one thing in the parentheses, so you have an h value here that is negative 2 because it's an x plus 3. So it's a negative 2 and a k value of 1. Now, what you're looking at here, you're plotting these graphs on the same one. It doesn't mean we're going to shift g of x. We're reusing the original function of f of x, okay? Because the parent function is still x cubed. I don't want you guys to think you shift what you just did. Okay? That would be weird. I hope none of you thought that, right?
It means like shift.
Yeah.
Oh, okay, I say, well, I'm taking the parent.
Yeah, always go back to the parent. Yeah. One of the greatest quote of the years, I think it was quote of the year, was a student yelled, "Bullshit, Jason." She got all smug. That was very funny. You were shifting things. She said, "Bullshit, Jason." They were arguing. Exactly. So here again, I go back to my parent function, and I start with, do I have to move left first or up first? Does it matter?
No, it doesn't.
It doesn't matter. As long as you move them both. Left 2, up 1. Left 2, up 1. Left 2, up 1. Left 2, up 1.
So wait, I have a question.
Yes, ma'am.
Are you Would that make us just be better?
I think the best things that I can do with this, these you should be able to.
I think we should be, because we're just like.
Because when you go back to thinking about graphing, if you're looking at a graph that is just x cubed, well, that all I can fit on my graph is -2, -1, 0, 1, and 2. I should be able to do that. Same thing with square root of x. Here I'm going to use 0, 1, 4, and 9. Let me use my perfect squares. If I do this, cube roots, what would you use for cube root for your values?
8 and 27.
0, 1, 8, 27. Obviously, the 27 is going to be tough to fit on there, but you can do 0, 1, and 8. I could also do -1, -8.
Yeah.
Because I can take a cube root of a negative because it's okay. It's an odd function, or not odd. It's an odd power that works itself through with the negatives. It's okay. All right. Those rational ones. That's a whole different ballgame, isn't it? That was the idea that could you plot the asymptotes correctly and then figure out where the curve goes. That's different. Okay, there's no real parent function going in on all of that. I don't know if we'll get into log graphs, or we'll probably wait to do those, the exponential ones, until later on. We're probably just going to stick with quadratics, square roots, cubes, cube roots, things like that for right now, just to remind ourselves how in the world does this work, okay? Let's try it out here.
Try 'em out.
Reflecting. Reflection. Reflection is just basically the A value in front is negative. It just goes the other way. That's it. So if your x squared parabola is up like a cup, what is the negative x squared parabola?
Down like a frown.
Down like a frown. If your x cubed function goes up like that, where does it go when it's negative?
Down. Yeah.
Switch your dance moves around.
Switch your things.
Okay? You just change direction.
That's how you're supposed to do it.
It's not like how you're supposed to give it.
Well,
Yeah.
song
Hey, you're dying!
the song is what I meant.
All it is you're just flipping it over. That's it. It's just a reflection. It just changes the direction. Okay? That's all it does. You knew that. Okay? If you have the square root of x,
Oh, yeah.
what does that look like? Do you remember? Where does the square root of x look like? Which way? Like going like this or to the left?
This way, I'm guessing.
Right.
Going to the right. Yeah, this one goes to the right. Now, what if it was this?
Other way. Other way.
Which other way? Now, what you're saying then,
Oh, wait.
think about if I went that way, I'd be taking square roots of negatives, wouldn't I?
Yeah. Wait.
So let me ask you this, order of operations.
So would it be like this?
Yes, very good. It would be this way. Okay. What happens here is that, and I'm glad you started to think about it, this graph, the negative x squared, cannot go to the left. The reason it can't go to left, because numbers to the left, if you started just at 0, would be -1. What's the square root of -1? I don't know.
I said 1, so I mean.
Trust me, it doesn't get better. It really doesn't. I'm running out of material real fast. So it's just the idea that you're just switching directions through,
Were you
okay?
like waiting for us to say that? Like, what if the whole class says 1 like I did, then you couldn't say your joke?
No, I believe it or not, I wing most of my jokes. I'm witty. I don't have these things. I don't go by script.
What?
Bless you. Yeah. I don't practice my material on my children at home. Hey Connor, did I ever tell you the one about the imaginary number?
You were sleepy.
He'll look at me like,
Go back to bed.
what are you talking about? Let's go play Legos.
You should like teach them like math like now, so they can be like.
You stepped on one?
He knows
I saw this thing.
They know how to.
It says,
They know how to add
Legos takes like
How old
1,200
are they?
pounds of
Well,
floor.
he's in first grade, like. He should know how to add.
That's how you make smart kids.
Let's do this. This is going to be in section 1.7. I forgot what page it's on. What I want you guys to do here is just kind of go through a couple of what are the graphs doing when they're shifted, and what are the parent functions, things like that. Ah, I see what you did there. Some random bullshit. That's good.
I thought you were actually.
Yeah, I thought it's not like
It's just funny because so. Oh my goodness. Sorry.
What's that?
Xena's so against
I know it's funny.
Oh, yeah, just go to this.
Let's see what it is.
What a silly man.
Dude,
He threw a ball in our way. From her shit. And about him being up like, oh, ball in the hallway.
It looks like a table.
Huh?
you know what? No. Sorry. You don't know that. Let's do 19.
That might be.
Also,
Whoa, man.
I want to. Oh.
That's Terrea.
Are you going full
Are you going to do this?
The last class.
Because I don't feel right now.
I have to go.
So I want you to try those. Okay. This is on page 81 in 1.7. The 19 through 33, excuse me. It's asking you to identify the parent function and then describe how it's being moved on the parent function. For example, on number 19, it says 12 minus x squared, function, whatever it was, g of x. Part A, what's the parent function?
X squared.
X squared. So the parent function here, I would say, is f of x is x squared. Now, what did they do to this function? Now, what I would do is I would rewrite it in that standardized form. I would rewrite this as negative x squared plus 12. What's your a value? Negative 1. So I know that in part B I can say that a is negative 1. What's h?
Wait, so if I like write this down.
Hold on, I can't. What's h? It's 0.
There is no.
There is no h, so h is 0, so there's no horizontal shift, and k is 12. So to the original function, you can say that it's been reflected and moved upward 12. Does that make sense? That's what you're looking to be able to do. I would try and figure out what your a, h's, and k's are. Remember that if a is negative, it's been flipped. If a is like, negative 3 means it's just been multiplied and it's gotten skinnier. The h's and the k tells you if you move left or right, up and down.
So
Okay?
if it's the original, like positive, and then the opposite is negative, it's been, or like the shift is negative.
Okay. There's a couple other parts that are on there. Basically, I just want you to identify the parent function and tell me how it's moved. That's it. Okay? Does that make sense? We'll worry about how you can write it in terms of each other later. Right now, I just want to know where did it go and how did it move. The last grouping is saying if x squared has been moved 2 units to the right and 8 units down, what's the new equation? Oh, that's easy. You should be able to do that real quick.
Honestly,
Okay? We'll do more of the actual physical plotting of stuff tomorrow. We'll get to some of the exponent stuff, okay? All right.
there's like courses that finish, but I don't